Hello, this is a reading of Database Systems, Chapter 1. Chapter 1 is an introduction to the entire book. So we're just going to start off with Chapter 1, Introduction. A database management system, DBMS, is a collection of interrelated data and a set of programs to access those data. The collection of data, usually referred to as the database, contains information relevant to an enterprise. The primary goal of a DBMS is to provide a way to store and retrieve database information that is both convenient and efficient. Database systems are designed to manage large bodies of information. Management of data involves both defining structures for storage of information and providing mechanisms for manipulation of information. In addition, the database system must ensure the safety of the information stored, despite system crashes or attempts at unauthorized access. If data are to be shared among several users, the system must avoid possible anomalous results. Because information is so important in most organizations, computer scientists have developed a large body of concepts and techniques for managing data. These concepts and techniques form the focus of this book. This chapter briefly introduces the principles of database systems. 1.1 Database System Applications. Databases are widely used. Here are some representative applications. Enterprise information, sales for customer product and purchase information, accounting for payments, receipts, account balances, assets, and other accounting information, human resources for information about employees, salaries, payroll taxes and benefits, and for the generation of paychecks, manufacturing for management of supply chain and for tracking production of items in factories, inventories of items in warehouses and stores, and orders for items. Online retailers for sales data noted above, plus online order tracking generation of recommendation lists and maintenance of online product evaluation, banking and finance, banking for customer information, accounts, loans, and banking transactions, credit card transactions for purchases on credit cards and generation of monthly statements, finance for storing information about holdings, sales, and purchases of financial instruments such as stocks and bonds, also for storing real-time market data to enable online trading by customers and automated training by the firm. Universities for student information, course registration, and grades, in addition to standard enterprise information such as human resources and accounting. Airlines for reservations and schedule information. Airlines were among the first to use databases in a geographically distributed manner. Telecommunication for keeping records of calls made, generating monthly bills, maintaining balances on prepaid calling cards, and storing information about the communication networks. As this list illustrates, databases form an essential part of every enterprise today, storing not only types of information that are common to most enterprises, but also information that is specific to category of the enterprise. Over the course of the last 4 decades of the 20th century, use of databases grew in all enterprises. In the early days, very few people interacted directly with database systems. Although, without realizing it, they interacted with databases indirectly through printed reports such as credit card statements, or through agents such as bank tellers or airline reservation agents. Then automated teller machines came along and let users interact directly with databases. Phone interfaces to computers, interactive voice response systems also allowed users to deal directly with databases, A caller could dial a number and press phone keys to enter information or to select alternative options to find flight, arrival, departure times, for example, or to register for courses in a university. The Internet revolution of the late 1990s sharply increased direct user access to databases. Organizations converted many of their phone interfaces to databases into web interfaces and made a variety of services and information available online. For instance, when you access an online bookstore or browse a book or a music collection, you're accessing data stored in the database. When you enter an order online, your order is stored in a database. When you access a bank website and retrieve your bank balance and transaction information, the information retrieved from the bank's database system. When you access a website, information about you may be retrieved from a database to select which advertisements you should see. Furthermore, data about your web access may be stored in a database. Thus, although user interfaces hide details of access to a database, and most people aren't aware they are dealing with a database, accessing databases forms an essential part of almost everyone's life today. The importance of database systems can be judged in another way today. Database system vendors like Oracle are among the largest software companies in the world, and database systems form an important part of product line of Microsoft and IBM. 1.2 Purpose of database systems. Database systems arose in response to early methods of computerized management of commercial data, and is an example of such methods typical of the 1960s, considered part of a university organization that, among other data, keeps information about all instructors, students, departments, and course offerings. One way to keep information on the computers is stored in the operating system files. To allow users to manipulate the information, the system has a number of applications programs to manipulate the files, including programs to add new students, instructors and courses, register students for courses and generate class reports, assign grades to students, compute grade point averages, and generate transcripts. System programmers wrote these application programs to meet the needs of the university. New applications programs are added to the system as the need arises. For example, suppose that a university decides to create a new major, say computer science. As a result, the university creates a new department and creates new permanent files or adds information to existing files to record information about the instructors in the department, students in the major course offerings, degree requirements, etc. The university may have to write new application programs to deal with these rules specific to the new major. New applications programs may also have to be written to handle new rules in the university. Thus, as time goes by, the system acquires more files and more application programs. This typical file processing system is supported by a conventional operating system. The system stores permanent records in various files, and it needs different application programs to extract records from and add records to the appropriate files. Before database management systems, DBMSs, were introduced, organizations usually stored information in such systems. Keeping organization information in a file processing system has a number of major disadvantages. Point 1. Data redundancy and inconsistency. Since different programs create the files and application programs over a long period, the various files are likely to have different structures and the programs may be written in several programming languages. Moreover, the same information may be duplicated in several places in files. For example, if a student has a double major, say music and mathematics, the address and telephone number of that student may appear in a file that consists of student records of students in the music department and in a file consisting of student records of students in the mathematics department. This redundancy leads to higher storage and access costs. In addition, it may lead to data inconsistency, that is, the various copies of the same data may no longer agree. For example, a changed student address may be reflected in the music department records, but not elsewhere in the system. Difficulty in accessing data. Okay, suppose that one of the university clerks needs to find out the names of all the students who live within a particular postal code area. The clerk asks the data processing department to generate such a list. Because the designers of the original system did not anticipate this request, there's no application program on hand to meet it. There is, however, an application program to generate the list of all students. The university clerk has now two choices: either obtain the list of all students and extract the needed information manually, or ask a programmer to write the necessary application program. Both alternatives are obviously unsatisfactory. Suppose that such a program is written and that several days later the same clerk needs to trim that list to include only those students who have at least 60 credit hours. As expected, a program to generate such a list does not exist. Again, the clerk has the preceding two options, neither of which is satisfactory. The point here is that conventional file processing environments do not allow needed data to be retrieved in convenient and efficient manner. More responsive data retrieval systems are required for general use. Data isolation. Because data are scattered in various files, and files may be in different formats, writing new application programs to retrieve appropriate data is difficult. Integrity problems. The data values stored in database must satisfy certain types of consistency constraints. Suppose the university maintains an account for each department and records the balance amount in each account. Suppose also that the university requires that the account balance of a department may never fall below zero. Developers enforce these constraints in the system by adding appropriate code in the various application programs. However, when new constraints are added, it is difficult to change the programs to enforce them. The problem is compounded when constraints involve several data items from different files. Atomicity problems. A computer system, like any other device, is subject to failure. In many applications, it is crucial that if a failure occurs, the data be restored to the consistent state that existed prior to the failure. Consider a program to transfer $500 from an account balance of Department A to the account balance of Department B. If a system failure occurs during the execution of the program, it is possible that the $500 was removed from the balance Department A, but was not credited to the balance Department B, resulting in an inconsistent database state. Clearly, it is essential to database consistency that either both the credit and debit occur, or that neither occur. That is, funds transfer must be atomic. It must happen in its entirety or not at all. It is difficult to ensure atomicity in a conventional file processing system. Concurrent access anomalies. For the sake of overall performance of the system and faster response, many systems allow multiple users to update the data simultaneously. Indeed, today, the largest internet retailers may have millions of accesses per day to their data by shoppers. In such environment, interaction of concurrent updates is possible and may result in inconsistent data. Consider Department A with an account balance of $10,000. If two department clerks debit the account balance by, say, $500 and $100, respectively, of Department A, and almost exactly the same time, the result of concurrent executions may leave the budget in an incorrect or inconsistent state. Suppose that the programs executing on behalf of such withdrawal read the old balance, reduce that value by the amount being withdrawn, and write the result back. If the two programs run concurrently, they may both read the value 10,000 and write back 9,500 and 9,900 respectively, depending on which one writes the value last. The account balance of Department A may contain either 9,500 or 9,900, rather than the correct value of 9,400. To guard against this possibility, the system must maintain some form of supervision. But supervision is difficult to provide because data may be accessed by many different application programs that have not been coordinated previously. As another example, suppose a registration program maintains the count of students registered for a class in order to enforce limits on the number of students registered. When a student registers, the program reads the current count for the courses, verifies that the count is not already at the limit, adds 1 to the count, and stores the count back in the database. Suppose 2 students register concurrently with the count at, say, 39. The 2 program executions may both read the value 39, and both would then write back 40, leading to an incorrect increase of only 1. Even though 2 students successfully registered for the course and the count should be 41, furthermore, suppose the course registration limit was 40 in the above case, both students would be able to register, leading to a violation of the limit of 40 students. Security problems. Not every user of the database system should be able to access all the data. For example, in a university, payroll personnel need to see only that part of the database that has financial information. They do not need access to information about academic records. But since application programs are added to the file processing system in an ad hoc manner, enforcing such security constraints is difficult. These difficulties, among others, prompted the development of database systems. In what follows, we shall see the concept of algorithms that enable database systems to solve problems with file processing systems. And most of this book, we use a university organization as a running example of a typical data processing application. 1.3. View of data. A database system is a collection of interrelated data and a set of programs that allow users to access and modify these data. A major purpose of database systems is to provide users with an abstract view of data. That is, a system hides certain details of how the data are stored and maintained. 1.3.1. Data abstraction. For the system to be usable, it must retrieve data efficiently. The need for efficiency has led designers to use complex data structures to represent data in the database. Since many database system users are not computer trained, developers hide the complexity from users through several levels of abstraction to simplify user interactions with the system. We have point 1, physical level, bullet 1, physical level. The lowest level of abstraction describes how the data are actually stored. The physical level describes complex low-level data structures in detail. Bullet 2, logical level. The next higher level of abstraction describes what data are stored in the database and what relationships exist among those data. The logical level thus describes the entire database in terms of a small number of relatively simple structures. Although implementation of the simple structure at the logical level may involve complex physical level structures, the user of the logical level does not need to be aware of this complexity. This is referred to as physical data independence. Database administrators who must decide what information to keep in the database use logical level of abstraction. Bullet 3, view level. The highest level of abstraction describes only part of the entire database. Even though the logical level user uses simpler structures, complexity remains because of the variety of information stored in a large database. Many users of the database system do not need all this information. Instead, they need to access only part of the database. The view level of abstraction exists to simplify their interaction with the system. The system may provide many views for the same database. Figure 1.1 shows the relationship among the 3 levels of abstraction. In analogy to the concept of data types in programming language may clarify the distinction among levels of abstraction. Many high-level programming languages support the notion of structured type. For example, we may describe a record as follows. Type instructor equals record, ID is char, name is char, department name is char, salary numeric N. Let's look at the view level. So in the view level, we have different views, view 1, view 2, view N, and then we move to the second state, which is the logical level, and then the physical level. So this code defines a new record type called instructor with 4 fields. Each field has a name and a type associated with it. A university organization may have several such record types, including department, course, student. Department with fields, department name, building, budget. Course with fields, course ID, title, department name, credits. Student with fields, ID, name, department name, total credits. At the physical level, an instructor, department, and student record can be described as a block of consecutive storage locations. The compiler hides this level of detail from programmers. Similarly, the database system hides many of the lowest level storage details from database programmers. Database administrators, on the other hand, may be aware of certain details of the physical organization of the data. There's just a little note. It says the actual type declaration depends on the language being used. C and C++ use struct declarations. Java does not have such a declaration, but a simple class can be defined to the same effect. At the logical level, each such record as described by a type of definition, as in the previous code segment, and in the interrelationship of these record types, is defined as well. Programmers using programming language work at this level of abstraction. Similarly, database administrators usually work at this level of abstraction. Finally, at the view level, computer users see a set of application programs that hide details of the data types. At the view level, several views of the database are defined, and a database user sees some or all of these views. In addition to hiding details of the logical level database, the views also provide a security mechanism to prevent users from accessing certain parts of the database. For example, clerks in the university register office can see only that part of the database that has information about students. They cannot access information about salaries of instructors. One point 3.2 Instances and schemas. Databases change over time. As information is inserted and deleted. The collection of information stored in a database at any particular moment is called an instance of the database. The overall design of the database is called the database schema. Schemas are changed infrequently, if at all. The concept of database schemas and instances can be understood by an analogy to a program written in a programming language. A database schema corresponds to the variable declaration along with the associated type definitions in the program. Each variable has a particular value at a given instant. The values of the variables in a program at a point in time correspond to an instance of a database schema. Database systems have several schemas, partitioned according to the levels of abstraction. The physical schema describes the database design at the physical level, while the logical schema describes the database design at the logical level. A database may also have several schemas at the view level, sometimes called subschemas, that describe different views of the database. Of these, the logical schema is by far the most important in terms of its effect on application programs. Such programmers construct applications by using the logical schema. The physical schema is hidden beneath the logical schema and can usually be changed easily without affecting application programs. Application programs are said to exhibit physical data independence if they do not depend on the physical schema, and thus need not be rewritten if the physical schema changes. We study languages for describing schemas after introducing the notion of data models in the next section. Data models. Underlying the structure of database in the data model, a collection of conceptual tools for describing data, data relationships, data semantics, and consistency constraints, a data model provides a way to describe the design of a database at the physical, logical, and view levels. There are a number of different data models that we shall cover in the text. The data models can be classified into 4 different categories. Relational model. The relational model uses a collection of tables to represent both data and the relationships among those data. Each table has multiple columns, and each column has a unique name. Tables are also known as relations. The relational model is an example of a record-based model. Record-based models are so named because the database is structured in fixed format records of several types. Each table contains records of a particular type. Each record type defines a fixed number of fields or attributes. The columns of the table corresponds to the attributes of the record type. The relational data model is the most widely used data model, and a vast majority of current database systems are based on the relational model. Chapter 2 through 8 cover the relational model in detail. The entity relationship model. The entity relationship ER data model uses a collection of basic objects called entities and relationships among these objects. An entity is a thing or object in the real world that is distinguishable from other objects. The entity relationship model is widely used in database design, and Chapter 7 explores it in detail. Object-based data model. Object-oriented programming, especially in Java, C++, or C#, has become the dominant software development methodology. This led to the development of object-oriented data model that can be seen as extending the ER model with notions of encapsulation. Methods, functions, or object entity. The object relational data model combines features of the object-oriented data model and relational data model. Chapter 22 examines the object relational data model. Semi-structured data model. The semi-structured data model permits the specification of data where individual data items of the same type may have different set of attributes. This is in contrast to the data models mentioned earlier, where every data item of a particular type must have the same set of attributes. The extensible markup language is widely used to represent semi-structured data. Chapter 23 covers it. Historically, the network data model and the hierarchical data model preceded the relational data model. These models were tied closely to the underlying implementation and complicated the task of model data. As a result, they are used little now, except in old database code that is still in service in some places. They are outlined online in Appendixes D and E for interested readers. Database languages. A database system provides a data definition language to specify the database schema and a data manipulation language to express database queries and updates. In practice, the data definition and data manipulation languages are not two separate languages. Instead, they simply form parts of a single database language, such as the widely used SQL language. Data manipulation language. A data manipulation language, DML, is a language that enables users to access or manipulate data as organized by the appropriate data model. The types of access are retrieval of information stored in the database, insertion of new information in the database, deletion of information from the database, modification of information stored in the database. There are basically two types. Procedural DMLs require a user to specify what data are needed and how to get those data, and declarative DMLs, also referred to as non-procedural DMLs, require a user to specify what data are needed without specifying how to get those data. Declarative DMLs are usually easier to learn and use than are procedural DMLs. However, since a user does not have to specify how to get the data, the database system has to figure out an efficient means of accessing data. A query is a statement requesting the retrieval of information. The portion of a DML that involves information retrieval is called a query language. Although technically incorrect, it is common practice to use the terms query language and data manipulation language synonymously. There are a number of database query languages in use, either commercially or experimentally. We studied the most widely used query language, SQL or SQL, in chapters 3, 4, and 5. We also studied some other query languages in chapter 6. The levels of abstraction that we discussed in section 1.3 apply not only to defining the structured data, but also to manipulating data. At the physical level, we must define algorithms that allow efficient access to data. At higher levels of abstraction, we emphasize ease of use. The goal is to allow humans to interact efficiently with the system. The query processor component of the database system, which we study in chapters 12 and 13, translates the DML queries into sequence of actions at the physical level of the database system. 1.42 Data Definition Language. We specify a database schema by a set of definition expressed by a special language called Data Definition Language, DDL. The DDL is also used to specify additional properties of the data. We specify the storage structure and access methods used by the database system by a set of statements in a special type of DDL called a Data Storage and Definition Language. These statements define the implementation details of the database schema, which are usually hidden from the users. The database values stored in the database must satisfy certain consistency constraints. For example, suppose the university requires that the account balance of a department must never be negative. The DDL provides facilities to specify such constraints. The database system checks these constraints every time the database is updated. In general, a constraint can be an arbitrary predicate pertaining to the database. However, arbitrary predicates may be costly to test. Thus, database systems implement integrity constraints that can be tested with minimum overhead. These are domain constraints. A domain of possible values must be associated with every attribute. For example, integer types, character types, datetime types. Declaring an attribute to be of particular domain acts as a constraint on the values that can take. Domain constraints are the most elementary form of integrity constraints. They are tested easily by the system whenever a new data item is entered into the database. Referential integrity. There are cases where we wish to ensure that a value that appears in one relation for a given set of attributes also appears in a certain set of attributes in another relation. Referential integrity, for example, the department listed for each course must be one that actually exists. More precisely, the department name value in a course record must appear in the department name attribute of some record of the department relation. Database modifications can cause violations of referential integrity. When a referential integrity constraint is violated, the normal procedure is to reject the action that caused the violation. Assertions. When assertions is any condition that the database must always satisfy. Domain constraints and referential integrity constraints are special forms of assertion. However, there are many constraints that we cannot express by using only these special forms. For example, every department must have at least 5 courses offered every semester. Must be expressed as an assertion. When an assertion is created, the system tests it for validity. If the assertion is valid, then any future modification to the database is allowed, only if it does not cause the assertion to be violated. Authorization. We may want to differentiate among the users as far as the type of access they are permitted on various data values in the database. These differentiations are expressed in terms of authorization, the most common being read authorization, which allows reading but not modification of data. Insert authorization, which allows insertion of new data but not modification of existing data. Update authorization, which allows modification but not deletion of data. And delete authorization, which allows deletion of data. We may assign the user all, none, or a combination of these types of authorization. The DDL, just like any other programming language, gets as input some instructions, statements, and generates some output. The output of the DDL is placed in the data dictionary, which contains metadata, that is, data about data. The data dictionary is considered to be a special type of data, a special type of table that can only be accessed and updated by the database system itself, not a regular user. The database system consults the data dictionary before reading or modifying actual data. Relational databases. A relational database is based on the relational model and uses a collection of tables to represent both data and the relationships among those data. It also includes a DML and a DDL. In Chapter 2, we present a general introduction to the fundamentals of the relational model. Most commercial relational database systems employ the SQL language, which we cover in great detail in chapters 3, 4, and 5. In chapter 6, we discuss other influential languages. 1.5.1 Tables. Each table has multiple columns, and each column has a unique name. Figure 1.2 presents a simple relational database comprising two tables. One shows details of university instructors, and the other shows details of the various university departments. The first table, the instructor table, shows, for example, that an instructor named Einstein with ID 22222 is a member of the physics department and has an annual salary of $95,000. The second table, department, shows that, for example, that the biology department is located in the Watson building and has a budget of $90,000. Of course, a real-world university would have many more departments and instructors. We use small tables in the text to illustrate concepts. A larger example for the same schema is available online. The relational model is an example of a record-based model. Record-based models are so named because the database is structured in fixed format records of several types. Each table contains records of a particular type. Each record type defines a fixed number of fields or attributes. The columns of the table correspond to the attributes of the record type. It is not hard to see how tables may be stored in files. For instance, a special character such as a comma may be used to delimit the different attributes of a record, and another special character such as a new line character may be used to delimit records. The relational model hides such low-level implementation details from database developers and users. We also know that it is possible to create schemas in the relational model that have problems such as unnecessarily duplicated information. For example, suppose we store the department budget as an attribute of the instructor record. Then, whenever the value of a particular budget, say that one of the physics department changes, that changes must be reflected in the records of all instructors associated with the physics department. In Chapter 8, we shall study how to distinguish good schema designs from bad schema designs. All right, let's view these tables again. The instructor table and the department table. (1.5.2) Data manipulation language. The SQL query language is non-procedural. A query takes as input several tables, possibly only one, and also returns a single table. Here's an example of a SQL query that finds the names of all instructors in the history department. Select instructor.name from instructor, where instructor.department equals, quote, history, semicolon. So we have select from where. The query specifies that those rows from the table instructor where the department name is history must be retrieved, and the name attribute of these rows must be displayed. More specifically, the result of executing this query is a table with a single column labeled name and a set of rows, each of which contains the name of an instructor whose department name is history. If the query is run on the table in figure 1.2, The result will consist of two rows, one with the name El-Sad and the other with the name Calafiri. So if we were to go back to figure 1.2, and I believe this is figure 1.2. And basically what they're saying is if we were to select the first table, instructor.name, so the instructor table by name, from instructor, where instructor.department name is history, we would get two different names, El-Sad and also Calafari. So our little query would report two rows. Queries may involve information from more than one table. For example, the following query finds the instructor ID and department name of all instructors associated with the department with a budget of greater than $95,000. So first we do select instructor.id, comma, department.department name. So we're actually selecting two tables. From instructor, comma, department, where instructor.department equals department.department name and department.budget is greater than $95,000. If the above query were run on tables in figure 1.2, the system will find that there are two departments with a budget of greater than $95,000, computer science and finance, and there are 5 instructors in those departments. Thus the result would consist of a table with 2 columns, ID and department, and the 5 rows. The ID and the departments would be returned. 1.5.3 Data Definition Language. SQL or SQL provides a rich DDL that allows one to define tables, integrity constraints, assertions, etc. For instance, the following SQL DDL statement defines the department table. Create table, department, and in parentheses we have department name, so char 20, building, char 15, budget, numeric 12, 2. Execution of the above DDL statement creates the department table with 3 columns, department name, building, and budget, each of which has a specific data type associated with it. We discussed data types in more detail in Chapter 3. In addition, the DDL statement updates the data dictionary, which contains metadata, which, as we know, is data about data. See section 1.4.2. The schema of a table is an example of metadata. Database access from application programs. SQL is not as powerful as a universal Turing machine. That is, there are some computations that are possible using a general-purpose programming language but are not possible using SQL. SQL also does not support actions such as input from users, output to displays, or communications over the network. Such computations and actions must be written in a host language such as C, C++, or Java, with embedded SQL queries that access the data in the database. Application programs are programs that are used to interact with the database in this fashion. Examples in a university system are programs that allow students to register for courses, generate class rosters, calculate student GPA, generate payroll checks, etc. To access database DML statements need to be executed from the host language. There are two ways to do this: by providing an application program interface, a set of procedures that can be used to send DML and DDL statements to the database and retrieve the result. The Open Database Connectivity (ODBC) standard for use with the C language is a commonly used application program interface standard. The Java Database Connectivity (JDBC) standard provides corresponding features to the Java language. By extending the host language syntax to embed DML calls within the host language program, usually a special character prefaces DML calls, and a preprocessor called the DML precompiler converts the DML statements to normal procedure calls in the host language. 1.6 Database systems, database design. Well, first, database systems are designed to manage large bodies of information. These large bodies of information do not exist in isolation. They are part of the operation of some enterprise whose end product may be information from the database, or may be some device or service for which the database plays only a supporting role. Database design mainly involves the design of the database schema. The design of a complete database application environment that meets the needs of the enterprise being modeled requires attention to a broader set of issues. In this text, we focus initially on the writing of database queries and the design of database schemas. Chapter 9 discusses the overall process of application design. 1.6.1 Design Process. A high-level data model provides the database designer with conceptual framework in which to specify the data requirements of the database users and how the database will be structured to fulfill these requirements. The initial phase of the database design, then, is to characterize fully the data needs of the prospective database users. The database designer needs to interact extensively with domain experts and users to carry out this task. The outcome of this phase is a specification of user requirements. Next, the designer chooses a data model, and by applying the concepts of the chosen data model, translates these requirements into a conceptual schema of the database. The schema developed at this conceptual design phase provides a detailed overview of the enterprise. The designer reviews the schema to confirm that all data requirements are indeed satisfied and are not in conflict with one another. The designer can also examine the design to remove any redundant features. The focus at this point is on describing the data and their relationships rather than on specifying physical storage details. In terms of the relational model, the conceptual design process involves decisions on what attributes we want to capture in the database and how to group these attributes to form various tables. The what part is basically a business decision, and we shall not discuss it further in this text. The how part is mainly a computer science problem. There are principally two ways to tackle the problem. The first one is to use the entity relationship model. The other is to employ a set of algorithms, collectively known as normalization, that takes as input the set of all attributes and generates a set of tables. A fully developed conceptual schema indicates the functional requirements of the enterprise. In a specification of functional requirements, users describe the kinds of operations or transactions that will be performed on the data. Example operations include modifying or updating data, searching for and retrieving specific data, and deleting data. At this stage of conceptual design, the designer can review the schema to ensure it meets functional requirements. The process of moving from an abstract data model to the implementation of the database proceeds in two final design phases. In the logical design phase, the designer maps the high-level conceptual schema onto the implementation data model of the database system that will be used. The designer uses the resultant system-specific database schema in the subsequent physical design phase, in which the physical features of the database are specified. These features include the form of file organization and the internal storage structures. They are discussed in Chapter 10. 1.6.2 Database Design for University Organization. To illustrate the design process, let us examine how a database for a university could be designed. The initial specification of user requirement may be based on interviews with the database users and on the designer's own analysis of the organization. The description that arises from the design phase serves as the basis for specifying the conceptual structure of the database. Here are the major characteristics of the university. The university is organized into departments. Each department is identified by a unique name, department name. It is located in a particular building and has a budget. Each department has a list of courses it offers. Each course has associated with it a course ID, title, department, and credits, and may also have associated prerequisites. Instructors are identified by their unique ID. Each instructor has a name, associated department, department name, and salary. Students are identified by their unique ID. Each student has a name, an associated major, department, and total credit hours the student earned thus far. The university maintains a list of classrooms, specifying the name of the building, room number, and room capacity. The university maintains a list of all classes, sections taught. Each section is identified by a course ID, section ID, year, and semester, and has associated with it a semester, a year, a building, a room number, a time slot ID. The time slot when the classes meets. The department has a list of teaching assignments specifying for each instructor the sections of the instructor is teaching. The university has a list of all students' course registrations, specifying for each student the courses and the associated sections that the students have registered for. A real university database would be much more complex than the preceding design. However, we use this simplified model to help you understand the conceptual ideas without getting lost in details of complex design. The entity relationship model. The entity relationship, ER, data model uses a collection of basic objects called entities and relationships among these objects. An entity is a thing or object in the real world that is distinguishable from other objects. For example, each person is an entity, and bank accounts can be considered as entities. Entities are described in a database by a set of attributes. For example, the attributes department name, building, budget may describe one particular department in a university, and they form attributes of the department entity set. Similarly, Attributes ID, name, and salary may describe an instructor entity. The extra attribute ID is used to identify an instructor uniquely, since it may be possible to have two instructors with the same name and the same salary. A unique instructor identifier must be assigned to each instructor. In the U.S., many organizations use the Social Security number of a person. A unique number the U.S. government assigns to every person in the U.S. as a unique identifier. A relationship is an association among several entities. For example, a member relationship associates with an instructor with her department. The set of all entities of the same type and the set of all relationships of the same type are termed an entity set and relationship set, respectively. The overall logical structure schema of a database can be expressed graphically by an entity relationship ER diagram. There are several ways in which to draw this diagram. One of the most popular is to use the Unified Modeling Language, UML. In the notation we use, which is based on UML, an ER diagram is represented as follows. A simple ER diagram. Here we have instructor that has the ID, the name, and the salary, and department table with the department name, bill, and budget. And this forms both connected as members of a simple ER diagram. Entity sets are represented by a rectangular box with the entity set name in the header and the attributes listed below it. Relationship sets are represented by a diamond connecting a pair of related entity sets. The name of the relationship is placed inside the diamond. As an illustration, consider part of a university database consisting of instructors and department with which they are associated. Figure 1.3 shows the corresponding ER diagram. The ER diagram indicates that there are two entity sets, instructor and department with attributes as outlined earlier. The diagram also shows the relationship member between instructor and department. In addition to entities and relationships, the ER model represents certain constraints to which the contents of a database must conform. One important constraint is mapping cardinalities, which express the number of entities to which another entity can be associated via a relationship set. For example, if an instructor must be associated with only a single department, the ER model can express that constraint. The entity relationship model is widely used in database design, and Chapter 7 explores it in detail. Normalization. Another method for designing a relational database is to use a process commonly known as normalization. The goal is to generate a set of relation schemas that allow us to store information without unnecessary redundancy, yet also allows us to retrieve information easily. The approach is to design schemas that are in appropriate normal form. To determine whether a relation schema is in one of the desired normal forms, we needed additional information about the real-world enterprise that we are modeling with the database. The most common approach is to use functional dependencies, which we cover in section 8.4. To understand the need for normalization, let us look at what can go wrong in a bad database design. Among the undesirable properties that a bad design may have are repetition of information, inability to represent certain information. So we have figure 1.4, the faculty table. We shall discuss these problems with the help of a modified database design for our university example. Suppose that instead of having two separate tables, instructor and department, we have a single table, faculty, that combines the information from the two tables. Notice that there are two rows in faculty that contain repeated information about history department, specifically that department's building and budget. The repetition of information in our alternative design is undesirable. Repeating information wastes space. Furthermore, it complicates updating the database. Suppose that we wish to change the data amount of the history department from 50,000 to 46,800. This change must be reflected in two ways. Contrast this with the original design, where this requires an update to only a single row. Thus, updates are more costly under the alternative design than under the original design. When we perform the update in the alternative database, we must ensure that every tuple pertaining to the history department is updated, or else our database will show the two different budget values for the history department. Now let us shift our attention to the issue of inability to represent certain information. Suppose we are creating a new department in the university. In the alternative design above, we cannot represent directly the information concerning the department name, bill, and budget, unless the department has at least one instructor at the university. This is because rows in the faculty department require values for ID, name, and salary. This means that we cannot record information about newly created department until the first instructor is hired for the new department. One solution to this problem is to introduce null values. The null value indicates that the value does not exist or is not known. An unknown value may be either missing, the value does not exist, but we do not have that information, or not known. We do not know whether or not the value actually exists. As we shall see later, null values are difficult to handle, and it is preferably not to resort to them. If we are not willing to deal with null values, then we can create a particular item of department information only when the department has at least one instructor associated with the department. Furthermore, we will have to delete this information when the last instructor in the department departs. Clearly, this situation is undesirable, since under our original database design, the department information would be available regardless of whether or not there is an instructor associated with the department, and without resorting to null values. An extensive theory of normalization has been developed that helps formally define what database designs are undesirable and how to obtain desirable designs. Chapter 8 covers relational database design, including normalization. Database storage and querying. A database system is partitioned into modules that deal with each of the responsibilities of the overall system. The functional components of a database system can be broadly divided into the storage manager and the query processor components. The storage manager is important because databases typically require a large amount of storage. Corporate database ranges in size from hundreds of gigabytes to, for the largest database, terabytes of data. A gigabyte is approximately 1,000 megabytes, actually 1,024. A billion bytes. A terabyte is 1,000,000 megabytes, 1,000,000,000,000 bytes. Since the main memory of computers cannot store this much information, the information is stored on disks. Data are moved between disk storage and main memory as needed. Since the movement of data to and from disks is slow relative to the speed of the central processing unit, it is imperative that the database system structure the data so as to minimize the need to move data between disk and main memory. The query processor is important because it helps the database system to simplify the facility access to data. The query processor allows database users to obtain good performance while being able to work at the view level and not be burdened with understanding the physical level details of the implementation of the system. It is the job of the database system to translate updates and queries written in a non-procedural language at the logical level into an efficient sequence of operations at the physical level. 1.7.1 Storage Manager. The Storage Manager is the component of the database system that provides the interface between the low-level data stored in the database and the application programs and queries submitted to the system. The Storage Manager is responsible for the interaction with the File Manager. The raw data are stored on the disk using the file system provided by the operating system. The Storage Manager translates the various DML statements into low-level file system commands. Thus, the Store Manager is responsible for storing, retrieving, and updating data in the database. The Storage Manager components include Authorization and Integrity Manager, which tests for the satisfaction of integrity constraints and checks the authority of the user to access the data. Transaction Manager, which ensures that the database remains in a consistent, correct state despite system failures and that concurrent transactions proceed without conflicting. A File Manager, which manages the allocation of space on the disk, storage, and data structures used to represent information stored on disk. The Buffer Manager, which is responsible for fetching data from disk storage into main memory and deciding what data to cache in main memory. The Buffer Manager is a critical part of the database system since it enables the database to handle data sizes that are much larger than the size of main memory. The Storage Manager implements several data structures as part of the physical system implementation. Data files, which stores the database itself. Data dictionary, which stores metadata about the structure of the database, in particular the schema of the database. And indices, which can provide fast access to data items like the index in this textbook. The database index provides pointers to those data items that hold a particular value. For example, we could use an index to find an instructor record with a particular ID, or all instructor records with a particular name. Hashing is an alternative to indexing that is faster in some, but not all cases. We discussed storage media, file structures, and buffer management in Chapter 10. Methods of accessing data efficiently via indexing or hashing are discussed in Chapter 11. The query processor. The query processor components include DDL interpreter, which interprets DDL statements and records the definitions in the data dictionary, and DML compiler, which translates DML statements in a query language into an evaluation plan consisting of low-level instructions that the query evaluation engine understands. A query can usually be translated into any number of alternative evaluation plans that are all given the same result. The DML compiler also performs query optimization. That is, it picks the lowest cost evaluation plan from among the alternatives. Query evaluation engine, which executes low-level instructions generated by the DML compiler. Query evaluations is covered in Chapter 12, while the methods by which the query optimizer chooses from among the possible evaluation strategies are discussed in Chapter 13. Transaction management. Often, several operations on the database form a single logical unit of work. An example is funds transfer, as in Section 1.2, in which one department account, say A, is debited from another department account, say B, is credited. Clearly, it is essential that either both the credit and debit occur or that neither occur. That is, the funds transfer must happen in its entirety or not at all. This all or nothing requirement is called automaticity. In addition, it is essential that the execution of the funds transfer preserve the consistency of the database. That is, the value of the sum of the balances of A and B must be preserved. This correctness requirement is called consistency. Finally, after the successful execution of funds transfer, the new values of balances of accounts A and B must persist despite the possibility of system failure. This persistence requirement is called durability. A transaction is a collection of operations that performs a single logical function in a database application. Each transaction is a unit of both autonomy and consistency. Thus, we require that transactions do not violate any database consistency constraints. That is, if the database was consistent when a transaction started, the database must be consistent when the transaction successfully terminates. However, during the execution of a transaction, it may be necessary temporarily to allow inconsistency, since either the debit of A or the credit of B must be done before the other. This temporary inconsistency, although necessary, may lead to difficulty if a failure occurs. It is the programmer's responsibility to define properly the various transactions so that each preserves the consistency of the database. For example, the transaction that transfers funds from the account of Department A to the account of Department B can be defined to be composed of two separate programs, one that debits account A and another that credits account B. The execution of these two programs, one after the other, will indeed preserve consistency. However, each program by itself does not transform the database from a consistent state to a new consistent state. Thus, these programs are not transactions. Ensuring the autonomicity and durability are to ensure the autonomy property. A failed transaction must have no effect on the state of the database. Thus, the database must be restored to the state in which it was before the transaction in question started executing. The database system must therefore perform failure recovery, that is, detect system failures and restore the database to the state that existed prior to the occurrence of the failure. Finally, when several transactions update the database concurrently, the consistency of the data may no longer be preserved, even though each individual transaction is correct. It is the responsibility of the concurrency control manager to control the interaction among the concurrent transactions to ensure the consistency of the database. The transaction manager consists of the concurrency control manager and the recovery manager. The basic concepts of transaction processing are covered in Chapter 14. The management of concurrent transactions is covered in Chapter 15. And Chapter 16 covers failure recovery in detail. The concept of transaction has been applied broadly in database systems and applications, while the initial use of transactions was in financial applications. The concept is now used in real-time applications in telecommunications as well as in management of long durations, activities such as product design or administrative workflows. These broader applications of the transaction concept are discussed in Chapter 26. Database architecture. We're now in a position to provide a single picture, Figure 1.5, of the various components of a database system and the connections among them. The architect of a database system is greatly influenced by the underlying computer system on which the database system runs. A database system can be centralized or client-server, where one server machine executes work on behalf of multiple client machines. A database system can also be designed to exploit parallel computer architectures. Distributed databases span multiple geographically separated machines. In Chapter 7, we cover the general structure of modern computer systems. In Chapter 18, describes how various actions of database, in particular query processing, can be implemented to exploit parallel processing. Chapter 19 presents a number of issues that arise in a distributed database and describe how to deal with each issue. The issues include how to store data, how to ensure autonomy of transactions that execute at multiple sites, how to perform concurrency control, and how to provide high availability in the presence of failures. Distributed query processing and directory systems are also described in this chapter. Most users of a database system today are not present at the site of the database system, but connect to it through a network. We can therefore differentiate between client machines on which remote database users work and server machines on which database systems run. Database applications are usually partitioned into 2 or 3 parts, as in Figure 1.6. In a 2-tiered architect, the application resides at the client machine, where it invokes database system functionality, and the server machine. First, Figure 1.5. We have the different users, the different applications, and how they use it. One 1.6, the 2-tier and 3-tier architect. We have a 2-tier, and 3-tier. We have application database system, application client, application server, and database system. In a 2-tier architect, the application resides at the client machine, where it invokes database system functionality at the server machine through query language statements. Application program interface standards like ODBC or GDBC are used for interaction between the client and the server. In contrast, in a 3-tier architect, the client machine acts as merely a front end and does not contain any direct database calls. Instead, the client end communicates with the application server, usually through a forms interface. The application server, in turn, communicates with the database system to access database data. The business logic of the application, which says what actions to carry out under what conditions, is embedded in the application server. Instead of being distributed across multiple clients, 3-tier applications are more appropriate for large applications and for applications that run on the World Wide Web. 1.10, data mining, information retrieval. The term data mining refers loosely to the process of semi-automatically analyzing large databases to find useful patterns, like knowledge discovery and artificial intelligence, also called machine learning, or statistical analysis. Data mining attempts to discover rules and patterns from data. However, data mining differs from machine learning and statistics in that it deals with large volumes of data, stored primarily on disk. That is, data mining deals with knowledge discovery in databases. Some types of knowledge discovered from a database can be represented by a set of rules. The following is an example of a rule stated informally. Young women with annual incomes greater than $50,000 are the most likely people to buy small sports cars. Of course, such rules are not universally true. but rather have degrees of support and confidence. Other types of knowledge are represented by equations relating different variables to each other, or by other mechanisms for predicting outcomes when the values of some variables are known. There are a variety of possible types of patterns that may be useful, and different techniques are used to find different types of patterns. In Chapter 20, we study a few examples of patterns, and we see how they may be automatically derived from a database. Usually there is a manual component of data mining consisting of pre-processing data to form acceptable to algorithms and post-processing of discovered patterns to find novel ones that could be useful. There may also be more than one type of pattern that can be discovered from a given database, and manual interaction may be needed to pick useful types of patterns. For this reason, data mining is really a semi-automatic process in real life. However, in our description, we concentrate on the automatic aspect of mining. Businesses have begun to exploit the bargaining data online to make better decisions about their activities, such as what items to stock and how best to target customers to increase sales. Many of their queries are rather complicated, however, and certain types of information cannot be extracted even by using SQL. Several techniques and tools are available to help with decision support. Several tools for data analysis allows analysis to view data in different ways. Other analysis tools pre-compute summaries of very large amounts of data in order to give fast responses to queries. The SQL standard contains additional constructs to support data analysis. Large companies have diverse sources of data that they need to use for making business decisions. To execute queries efficiently on such diverse data, companies have built data warehouses. Data warehouses gather data from multiple sources under a unified schema at a single site. Thus, they provide the user a single uniform interface to data. Textual data, too, has grown explosively. Textual data is unstructured, unlike the rigidly structured data in relational databases. Querying of unstructured textual data is referred to as information retrieval. Information retrieval systems have much in common with database systems, in particular the storage and retrieval of data on secondary storage. However, the emphasis in the field of the information systems is different from that in database systems concentrating on issues such as querying based on keywords, the relevance of documents that query, and the analysis, classification, and indexes of documents. In Chapter 20 and 21, we cover decision support, including online analytical processing, data mining, data warehousing, and information retrieval. Several application areas for database systems are limited. Section 1.11, Specialty Databases, it says several applications areas for database systems are limited by restrictions of the relational data model. As a result, researchers have developed several data models to deal with these application domains, including object-based data models and semi-structured data models. 1.11.1 Object-based data models. Object-oriented programming has become the dominant software development methodology. This led to the development of an object-oriented data model that can be seen as extending the ER model with notions of encapsulation methods, functions, and object identity, inheritance, object identity, and encapsulation, information hiding, with methods to provide information to objects are among the key concepts of object-oriented programming that have found applications in data modeling. The object-oriented data model also supports a rich type system, including structured and collection types. In the 1980s, Several database systems based on the object-oriented data model were developed. The major database vendors presently support the Object Relational Data Model, a data model that combines features of the object-oriented data model and relational data model. It extends the traditional relational model with a variety of features such as structured and collection types, as well as object orientation. Chapter 22 examines the object relational model. Semi-structured data models. Semi-structured data model permits the specification of data where individual data items of the same type may have different sets of attributes. This is in contrast with the data models mentioned earlier, where every data item of a particular type must have the same set of attributes. The XML language was initially designed as a way of adding markup information to text documents, but has become important because of its applications in data exchange. XML provides a way to represent data that has nested structure and furthermore allows a great deal of flexibility in structuring of data, which is important for certain kinds of non-traditional data. Chapter 23 describes the XML language, different ways of expressing queries on data represented in XML, and transforming XML data from one form to another. 1.12 Database users and administrators. A primary goal of database system is to retrieve information from and store new information into the database. People who work with the database can be categorized as database users or database administrators. 1.12.1 Database users and users interfaces. There are 4 different types of database system users, differentiated by the way they expect to interact with the system. Different types of users interface have been designed for different types of users. The naive user are unsophisticated users who interact with the system by invoking one of the application programs that have been written previously. For example, a clerk in the university who needs to add a new student, a new instructor to department invokes a program called New Hire. This program asks the clerk for the name of the instructor, her new ID, the name of the department, that is A, and the salary. The typical user interface for naive users is a forms interface where the user can fill in appropriate fields of the form. Naive users may also simply read reports generated from the database. As another example, consider a student who during class registration period wishes to register for a class by using a web interface. Such a user connects to a web application program that runs at a web server. The application first verifies the identity of the user and allows her to access a form where she enters the desired information. The form information is sent back to the web application at the server, which then determines if there is room in the class by retrieving information from the database, and if so, adds the student information to the class roster in the database. Application programmers. Application programmers are computer professionals who write application programs. Application programmers can choose from many tools to develop user interfaces. Rapid application development. Tools are tools that enable an application programmer to construct forms and reports with minimal programming effort. Sophisticated users interact with the system without writing programs. Instead, they form their requests either using the database query language or by using tools such as database analysis software. Analysts who submit queries to explore data in the database fall in this category. Specialized users are sophisticated users who write specialized database applications that do not fit into traditional data processing framework. Among these applications are computer-aided design systems, knowledge base and expert systems, systems that store data with complex data types, for example, graphics data and audio data, and environment modeling systems. Chapter 22 covers several of these applications. 112.2 Database Administrator. One of the main reasons for using DBMSs is to have central control of both the data and the programs that access those data. A person who has central control over the system is called a database administrator, a DBA. The function of a DBA includes schema definition. The DBA creates the original database schema by executing a set of data definition statements in the DDL. Storage structure and access method definition. Schema and physical organization modification. The DBA carries out changes to the schema and physical organization to reflect the changing needs of the organization or to alter the physical organization and improve performance. Granting of authorization of data access. By granting different types of authorization, the database administrator can regulate which parts of the database various users can access. The authorization information is kept in a special system structure that the database system consults whenever someone attempts to access the data in the system. And routine maintenance. Examples of database administrators' routine maintenance activities are periodically backing up the database, either onto tapes or onto remote servers to prevent loss of data in case of disasters such as flooding, ensuring that enough free disk space is available for normal operations and upgrading disk space as required, monitoring jobs running on the database and ensuring that performance is not degrading by various expensive tasks submitted by some users. Okay, we're going to finish up the rest of this. 1.13 talks about the history of database systems. Information processing drives the growth of computers as it has for the earliest days of commercial computers. In fact, automation of data processing types predates computers. Punch cards, invented by Herman, were used at the very beginning of the 20th century for U.S. Census data, and mechanical systems were used to process the cards and tabulate results. Punch cards were later widely used as a means of entering data into computers. Techniques for data storage and processing have evolved over the years. I'm not going to go too deep into the history of databases. This is really good, juicy stuff. We're going to fast forward to the summary. A database management system, DBMS, consists of a collection of interrelated data and collection programs to access the data. The data describe one particular enterprise. The primary goal of a DBMS is to provide an environment that is both convenient and efficient for people to use in retrieving and storing information. Database systems are ubiquitous today, and most people interact either directly or indirectly with databases many times every day. Database systems are designed to store large bodies of information. The management of data involves both the definition of structures for the storage of the information and the provision of informations for the manipulation of information. In addition, the database system must provide for the safety of the information stored. In the face of system crashes or attempts or at unauthorized access, if data are to be shared among several users, the system must avoid possible anomalous results. There are quite a lot of other summaries. The major purpose of database systems is to provide users with an abstract view of data. That is, the system hides certain details of how the data are stored and maintained. Underlying the structure of database is the data model, a collection of conceptual tools for describing data, data relationship, data semantics, data constraints. The relationship data model is the most widely deployed model for storing data in databases. Other data models are object-oriented model, the object relational model, and semi-structured data models. The DML, the DDL, DML is the language that enables users to access or manipulate data. Non-procedural DMLs, which require users to specify only what data are needed without specifying exactly how to get those data, are widely used today. A DDL is a language for specifying the database schema and as well as other properties of the data. Database design mainly involves the design of the database schema. The entity relationship ER data model is widely used data model for database design. It provides a convenient graphical representation of viewed data, relationships, and constraints. A database system has several subsystems: the storage manager, the query processor, transaction management. The architect of the database is greatly influenced by the underlying computer system in which the database system runs. The database applications are typically broken up into the front-end part that runs in the client machines. Knowledge discovery techniques attempt to discover automatically statistical rules and patterns from the data. And there are 4 different types of database systems, differentiated by the way they expect to interact with the system. That is a summary of the review of the terms. There are other terms that need to be defined, possibly in your own words. And then there are a list of practice exercises as well as the real exercises. And then finally, certain tools, notes, and that concludes Chapter 1.